Hello everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements. And here's another video in our FEA101 series, which is an introduction to FEA for new users. And this is the seventh video in the series, and we're looking again at the theoretical overview. And this time we're introducing dynamic and nonlinear effects into our theoretical overview. So just to do a quick review then from the last video of the minimum potential energy method, where we introduced the minimum potential energy method and we gave the general form of the equation as follows, which is roughly speaking broken down into a strain energy term and an external work term. And we went through how we can discretize that equation so it can be used with finite elements. We got it into this form here. And we talked about how we ended up with essentially a D matrix, which is a material property matrix, a B matrix, which is a strain displacement matrix, various force vectors according to a body force, surface forces, or point forces, the shape functions from the element type we picked, and we just outlined how U is the nodal displacement vector, and essentially U is what we're trying to find out. So we will know pretty much everything else in this equation when we make an FEA, and we're trying to find out what U is. And then at the end of the last video we talked about, well, it's common practice to group the force terms together. So we have the body force, the surface force, and the point force, and we group those together into a global force vector. So an important point here is if you look at the body force term here, and we take that out and just take a look at that by itself, it looks like this. So basically it's a summation across all the elements, integration across the volume of each element, the shape function multiplied by the body force that's applied to that element. So that's important because we're going to be adapting this term in the next couple of slides. And we said it's also, so first of all, a common practice to group force terms, but it's also a common practice to group these terms together, the B dB terms together, into what's called a stiffness matrix. So we can say that K, the stiffness matrix, is essentially this part of the equation here, so the BdB part. And when we do that, then the above equation, so this minimum potential energy equation, becomes a half U transpose K U minus U transpose times F. So essentially we're left with the stiffness matrix, the global force vector, and the nodal displacement vector, which we're trying to solve for. So as we discussed at the end of the last video, then minimizing this equation basically at the nodes ends up giving us our equation of static equilibrium, which is K times U is equal to F. In other words, stiffness matrix times nodal displacement vector is equal to the global force vector. So now let's talk about introducing dynamic effects. So again, just rephrasing that, K times U is equal to F is a statement of static equilibrium of the finite element mesh. However, applied forces may vary with time, which means that the displacements will also vary with time. So in this case, K times U is equal to F is a statement of static equilibrium at a specific point in time rather than throughout the entire problem. So in a static problem, K times U is equal to F holds for the entire problem, but in a dynamic problem, K times U is equal to F is only at a specific point of time. So in reality, if loads are applied quickly, inertia forces must be considered and a dynamic problem must be solved. And we can use Delambray's principle to include inertia forces as part of the body forces. So if you just recall, Delambray's principle basically says that an accelerating body can be transformed into an equivalent static system by adding an inertia force in the direction opposite to the motion, which acts through the center of mass. So in our case, we had the body force here, being just the shape function times the applied body force. But now we have that same term here, shape function times the applied body force. But we also have this new term in here, which has the mass density of the element m here and the acceleration here, nodal point acceleration. So we've introduced this term, okay, according to Delambray's principle, which we're putting a negative force acting in the opposite direction to the body force, if you like. So now our equilibrium equation becomes mu dot dot plus K times U is equal to F. In other words, mass matrix times nodal acceleration vector plus stiffness matrix times nodal displacement vector is equal to the applied force vector. So again, we have mu dot dot plus K times U is equal to F, where K is the global stiffness matrix as before, and now M is the global mass matrix. And the global mass matrix again is given by the mass density here and the shape function transpose multiplied by the shape function. And again, that's all integrated over the volume of each element and summed up for each element. So we've introduced mass and we've got acceleration, but it's very important to note that if we set something vibrating, so energy is always dissipated during vibration, and this is usually accounted for by a velocity dependent damping force. So we're now introduced damping forces as additional contributions to the body forces. So again, we're going to put much as we did with the acceleration, we're going to put in the damping force now as well with the body force. So now we've introduced this extra term on the end here. So initially we just had FB times S, which is the body force. Now we've introduced this additional, or in the last step we introduced this additional term here to take account of the mass. And now we're putting another term in here to take account of the damping. So the mass term goes with acceleration, and the damping term goes with velocity. So again, in this case, we have a damping parameter c and that cm is for element number n. So we can have a different one for each element. And then u dot is the nodal point velocities. Okay, so it's a vector of nodal velocities. So now our equation of equilibrium becomes mass times acceleration plus damping times velocity plus stiffness times displacement is equal to force. And again, mass is a matrix. Acceleration is a vector, so it's a vector of nodal accelerations. Again, C is the damping matrix, U is the vector of nodal velocities, K is the stiffness matrix, U is a vector of nodal displacements, and F is the global force vector. So again, just to clarify what C is going to be the damping parameter multiplied by the shape function for the element, the transpose of the shape function. Okay, so now we've gotten to the stage where we have our minimum potential energy method. Before it worked for just static equilibrium. Now we've introduced dynamic effects by essentially changing the body forces. So by using Delambre principle, we've added two additional terms into the body force. This term here, which deals with mass and acceleration, and this term here, which deals with damping and velocity. Okay, so the next thing we want to talk about then is introducing nonlinearity in finite element analysis. Okay, so far we've assumed that the displacements of the nodes in the finite element model were small. We assumed that the material was linear elastic, and we assumed that the boundary conditions remain unchanged during the application of loads. And just to be clear as to how that entered what we've done so far and how those assumptions went into the equilibrium conditions. So up to now, all integrations were performed over the original volume of the element, so that must mean that displacements must be small. So basically the volume hasn't changed very much, and this affects the K matrix and the F vector. We also assumed the strain displacement matrix was constant and independent of element displacements. Again, that didn't change throughout the solution. And the assumption of a linear elastic material is implied in the use of a constant material matrix D. So you might remember from the previous video we assigned D, which was just basically values of Young's modulus and Poisson's ratio, and it was essentially Hooke's law in 3 dimensions. And the unchanged boundary conditions are implied by keeping constant constraint relations for the complete response. So in other words, the boundary conditions aren't changing during the solution. So these 4 then give rise to the different types of nonlinearity that may arise in FEA. So the first one is nonlinearity due to large displacement, large rotation, and small strains. So again, we're getting a large displacement, we're getting a large moving of the model about the place, but maybe we're getting quite small strains, so it's not changing its shape very much, but it's moving around a lot. Next one is nonlinearity due to large displacement, large rotation, and large strains. So again, it's moving around quite a bit, but it's also changing its shape quite a bit because we've got large strains. The next one is material nonlinearity. Okay, so we don't have to use a linear material that obeys Hooke's law. We can use different types of material. And the last one is really concerned with contact, but also has includes some special cases like follower loads and things like that. So these first 2 here are often grouped together and are called geometric nonlinearities. And essentially what these are both saying is that the geometry changes under load, or due to the applied load we get significant changes in the geometry. And again, the last one here, the contact, is essentially saying that the load changes with deformation. So if you think about contact, we have 2 bodies touching off each other. as one of them deforms, the way the load is applied to that particular geometry is going to change. And the material nonlinearity is kind of self-explanatory. So let's just take a quick look at these. What we now have is three, so we're going to put these two together into geometric. We have material, and then we have contact. So geometric, when this becomes important, is when we have things like deflection of a beam that is greater than half the thickness of the beam. Anytime we have strains that are greater than 5%, or if we have deformation of a geometry that's bigger than 1/20th of the largest dimension of the geometry. So these are kind of guidelines as to when a geometric nonlinear analysis is required. Also things like buckling are a really good example of a geometric nonlinearity. And we're going to be talking about these in detail as we move further on in this course and we talk about modeling different problems. In terms of material nonlinearity then, so obviously if we don't have a linear elastic material, we can have a nonlinear elastic material, and we talked about this back in video number 3, I think, where we were looking at the fundamentals of stress and strain. We can also have elastoplastic materials, where things like metals, example of non-linear elastic materials are things like rubbers and polymers, foams, things like that. Elastoplastic materials, metals, where we have an elastic response and a plastic response. Also things like viscoelasticity, viscoplasticity, creep, etc. So they will all be non-linear material behavior. And then contact, so a good example of contact is things like trying to build a finite element model of metal forming. So we have dies touching off workpieces and deforming the workpieces, and we've, the boundary conditions are very much changing over time. Things like bolted joints, and also things like follower forces. So that's a force that essentially doesn't just act in one direction, it maybe stays perpendicular to a certain edge or something like that. And again, we'll look at examples of this as we go further into this course. So that's it for today. It's a reasonably short video. We just showed how we can introduce dynamic effects into our minimum potential energy formulation, and we had a brief review of the various types of nonlinearity that can arise in FEA and how they arise, and just some examples of those. So again, as usual, if you want more information, please do go and get a copy of the book. There's a lot more information in there. And that's the end of our video today, just introducing dynamic and nonlinear problems into the FEA method. And I'll see you in the next video.